Okay, so today we are going to begin something quite different, which has to do with classification. So basically deciding whether or not a document is relevant for a given query. Okay, so we'll first introduce the problem in general, and then we will begin with one of the first techniques that can be used to this purpose. Okay, so let's try to first understand why classification is an important task. So I guess have you any general idea of what classification is? Yeah? Image classification or text classification and so on. So you have a general understanding. Great. Now, we will specifically look at text classification, and this will also give us, let's say, a way to introduce a number of general techniques. Okay? So the first technique I'm going to introduce today is a statistical technique. Bias, Bias, naive. Have you already seen this? Where, Aris? Machine learning. So naive bias, already. Okay, so that's even better. Today we are going to see how you apply naive bias to text classification. Perhaps you were considering naive bias for image recognition, right? Machine learning, robots. Also for text? So you know already, so I can just go away. Today's lecture is cancelled because of students' knowledge. Okay, at worst it's good to revisit certain things you have already seen, from a different angle. So, let's begin with a classical problem, what is called standing queries. What is a standing query? Suppose that you set a Google alert, You want to be notified by Google whenever a new document, whatever document, it can even be a video, related to some topic of interest is indexed, right? So, for example, you are interested in motorbikes, and you could be interested in being notified about any new document containing, I don't know, the words bike and Yamaha, for example. So what can you do with Google Alerts is that you just specify one query, Q, like this. So this is called a standing query. So it's a query that is going to be there in the system, and periodically the system is going to check for new documents matching the query. Okay? So this is a bit different from what we have seen so far, right? There you have already indexed documents, and you get a query, and then based on your index you want to return the most relevant documents for the query. In this case, what is the situation? You already have a collection of documents from which you can learn in some way, and then a new document arrives, and you have to classify the document, whether or not this document is relevant for a given query. This automatically creates an implicit partition of the documents you have into two sets, the ones which are relevant for the query and the ones which are not. So, how do you handle standing queries? Well, actually, if you go back to the story of search engines, there have been a number of ways to address this. To begin with, manually. Okay, so you have people, let's say, writing pieces of software that will select documents that are likely to be relevant for the query. So essentially you expand the query to try and match potentially relevant documents with the highest accuracy possible. That's an example of Google Alerts. Another case in which you can view things as standing queries is, for example, spam filtering. So this case is already a bit different, and in a way it emphasizes the problems that you may have if you try to do things, let's say, manually. For example, you can give yourselves a definition of what a spam document is. For example, it could be a document containing certain occurrences of words or coming from certain email addresses and so on, right? So you begin with a query, but then eventually the spammers make their way through the spam filter, and then you try to refine your query and so on, right? So how is the system going to work actually? Normally, you don't try the query explicitly, but what you do is just you click on an email considering it as spam, and then the system, based on the on the document features, on the emails features, try to build a query that describes whatever you have considered to be spam, right? So it will build increasingly complex definitions of spam emails. At least this was the idea once, but then people, tried to leverage, let's say, machine learning techniques. So you don't explicitly build a query, but you do the following. For example, if I am categorizing as a human, let's say, queries that in my opinion are spam and which are not spam, I'm implicitly I'm doing two things. First of all, I'm categorizing them, the emails myself. Secondly, so I create a partition, two classes of documents, which are implicitly defined by my actions. And the second point I'm doing is I am creating a training set collection, right? You know what a training set is, roughly. So a training set is a collection, say, of documents that you can use to train a machine learning algorithm, which you are then going to use on a test set. So in this case, the training set, at every point in time, will be the set of emails which I have classified as spam or non-spam, implicitly. And the test set consists of all the new emails that I receive at any given point in time. Okay. So let us now, we have to begin some point in some way, right? So you have many things to classify. They can be images, videos, they can be audio files. Let's begin with something a bit simpler now. Text classification, right? So it is also, sometimes you find other terminology, different terminology like text categorization or filtering or whatever. They are, let's say, synonyms for the same meaning, so classification. At some point, I will have to make clear the distinction between, me or my Professor Vitaletti, between classification and clustering. But the purpose is the same, the means are different. But for the moment, let's stick to classification. The implicit idea behind classification is that normally you have a base of documents from which you can learn. Okay, so you have essentially a set of documents and a ground truth, which means that every document is labeled as relevant or non-relevant with respect to anything. You are interested in Chinese food, then you will have documents, a base of training documents, each of which is either relevant for Chinese food or not. But think always of this point. You have, first of all, a training set. How can we use it? Well, today we start to see one way in which we can use it, which is also very interesting because it is related to what are called probabilistic language models. So to models that in a way should describe how a document is generated. Okay? We will see that whenever you apply a bias classification, let alone a naive bias classification to a document corpus, you are implicitly assuming a model whereby, a probabilistic model whereby documents are generated. Okay? So in order to apply naive Bayes, we need to revisit a couple of things. What is the first thing we have to revisit? What do you think? Bayes theorem, right? Huh? So Bayes theorem has to do with computing marginal probabilities of conditioned events. Now, let us assume that you had two events. Two events could be, let's call them A and B. For example, A might be the weather is cloudy today. I'm just inventing. Event B might be rainy weather. So whenever you define events, you are implicitly defined as, an experiment. For example, the experiment might be at 11 o'clock sharp, I look at the weather. I'm not interested in sunny days like this, but whenever the day is cloudy, I will also check if it is raining or not at 11 sharp. These are my experiments that correspond to these events, for example. Once you have these experiments, you may be interested in asking, what is the probability, for example, that on any given day at 11 o'clock, it is going to rain given that the weather is cloudy? We use this notation. So how would I compute this probability? I don't know. I repeat the experiment 100 times, and then I take frequencies, right? That's my estimate of this probability. There would be a lot to say on how you estimate probabilities, but let's go with the intuition for the moment. As long as it makes intuitively sense to you, I'm fine. This is not a probability course. But what can you say about this probability? You can just apply the definitions and you know that this is true, right? From this, for example, you can apply what is called Bayes rule. If I know at some point the conditional probability that it is raining given, I should have chosen the other option. I should have chosen A condition to B, but it's fine. But now I think you will explain to me why that would have been a better idea. Anyway, what is the probability that B happens given A? This probability is defined in this following way. This means conjunction, right? So it is cloudy and it is raining, divided by the probability of the conditioning event, which is just a normalization. And if you just elaborate on this formula, you can still develop this as just applying definition. Notice I am assuming nothing about independence, no independence hypothesis. Also because with two such events, saying that they are independent would be a bit, let's say, bold. Okay? From this, at this point you can compute the conditional expectation of A condition to B given the other event. And that is Bayes rule. Now, what is this telling in our case? The probability that it is cloudy weather given that it is raining is equal to this. In this case, we know that this probability should be 1 already, but just because that's why I was saying maybe I should have defined A and B in the opposite way, because this is always true. But let's say if in this specific case the result is not 1, there is something strange, okay? I don't know of any day in which it is raining without clouds. Maybe it can happen. Maybe the clouds are somewhere else and there is a strong wind. Okay, so perhaps it is not completely stupid. That's Bayes' rule. Is everyone fine with this? Yeah? Great. You still have recollections from your basic probability course. Now, there is another thing that we may have to see at some point, which is the following. Let's say that you have, okay, the conjunction. I'm just trying to stick to the conventions used in the book. I don't like them very much, the way of writing probabilities, but that's the way, that is, let's say in machine learning, that's very often the way in which probabilities are written. Okay, so I will stick to them. I put a comma. So this is the conjunction of 4 events. What is this probability? You can write it as a product, even when the events are dependent. Okay, how? Do you agree with me up to this point? And then you can do the same with this, iteratively. So eventually, if you do this several times, eventually you will get okay? This is always true. Of course, I did it for 4 events. You can do it for an arbitrary number of events. Notice that I am doing no assumption here, whatever. I'm just considering the fact that these are also events, and it is a conjunction of events. So I'm just applying definitions of conditional probabilities. Okay? Notice another thing, that here I developed this product in this way. So first conditioning with respect to A2, A3, A4, but I could change the order. So I could write this as probability of A2 conditioned to A1, A3, and A4, and so on. Yes?
Aren't we miss a piece?
Sorry?
Aren't we miss probability of A4?
Yeah, sure. Great. Yes, of course. Okay, so what I want to say is that you can switch the order. This is just one example. And you always get the same result. So this expansion itself, is it useful or not? As we will see, it is useful, especially if we can simplify it and put some independence condition at some point. Okay? Then it becomes very useful. Everyone okay so far? We are not going to need much more than this. But it's important that you know what we need. Now, so we can go back to our lecture. What does it mean to categorize or classify a corpus of documents? So first of all, let's try to clarify the language they use, because sometimes the language doesn't help a lot to understand. For example, let's say you have something to classify. For us, something to classify will be a document with respect to a set of categories. For example, Chinese food, motorbikes, housing, and so on. So you're given a document and you want to automatically assign this document to one of the classes. Of course, the first problem is that sometimes a document can belong to more than one class, right? So to begin with, we consider the simple case in which you just have one document will belong to one class. Maybe it also should belong to other classes, but let's say that you try to assign it to the class which is more likely, or let's say that is the most important for the document, okay? In other cases, you are proceeding differently, but in these problems, when you start approaching them, it is a good idea to begin from simple cases, try to make your way, try to understand, and then perhaps you expand. You try to generalize, not the other way down, not the other way around, because otherwise you will not get anywhere. I mean, in research, normally that's what you do. So we are given a set of classes, and we are given the description of one instance. So what is one instance here? What is one instance? Oh. For us, we have documents. So one instance in our case will be a description of the document in some way. For example, if we use the document can be a bag of words describing the document, or the vector that corresponds to the document described with respect to a certain dictionary. That could be a document. Depends on actually it depends on the type of strategy we use. It could even be just a binary vector in which you have one component per word, per possible term appearing in the document, and you have a 1 if the document appears in the document, if the term appears in the document, 0 otherwise. Okay? So you have many choices. We will consider at least a couple of them in this lecture. So a description of the document for us will probably, today, it will be a vector. I'm not specifying further. The type of vector we consider will depend on the technique we use. Anyway, what we know already is that we are going to have a high-dimensional space, right? Text, words, the number of dimension is probably at least the number of words in the vocabulary, so that's a high-dimensional space. Get used to having to deal with high-dimensional spaces, okay? They're the most troublesome, and they're the most frequent in applications. And then we have a fixed set of classes. So in a way, we already know which classes we might be interested in. How can I define new classes? That's a different problem. Actually, that is where you normally introduce something called clustering. Okay? But our basic problem is the following. Given the set of classes and given an instance, so document in our case, or better, its representation, we want to decide one class. So we want to assign the document to one class. For example, this class might be the most likely class according to some probabilistic model. Okay? But consider what we are trying to do, what we are trying to do here. This is the problem we want to solve eventually. Okay? Now let's take one step back and think of which is the input we have and which is the output of anything we want to do. And I'm speaking of the learning algorithm. How do we learn to classify documents and assign them to one class? Can you make a conjecture? Try to, since you studied machine learning already. So we want to produce a machine learning algorithm. So what is the input we have and what is the output we want to produce? Try to abstract the problem. We don't just want to classify one document, right? We want to classify every possible document. So, what do we want to build? So this is a function that given this function, given one document, will eventually attribute it a class. Have we got this function? at the beginning? No. Actually, this is the output of the learning algorithm, okay? We want to compute this function. Of course, how many functions can I think of? Infinite functions. So I will pick one type, for example, one family of function, I don't know, characterized by coefficients, and try to compute the coefficients. That means deriving the function. And what information am I going to use to learn the classification function? What am I going to use?
Instance. Input.
Yeah, the input. What am I using? Something you must have, otherwise you're not going anywhere. The training set, right? I have a training set. Okay, whenever you're doing classification, you have a training set. No training set, no algorithm. Okay, and that is the reason why classification is called a supervised learning task. Supervised means that you essentially have a ground truth. You have a collection of documents, each document labeled with a correct class, and you are then trying to train your algorithm on that training set in order to learn this function. That's basically machine learning, right? In a summary, supervised machine learning. Supervised. There is unsupervised. But this is supervised, okay? So text classification is supervised. Naive Bayes classification, it is supervised. So you need a training set. For the moment, this is the most important thing to remember. This raises a number of problems. How you collect the training set, how you update it, and so on. We have seen, for example, that in the email case, email spamming case, you are collecting the training set implicitly. The more the user clicks on spam emails, the more the system learns. And that's very often the case why your spam filter improves its performance with time. I mean, if you don't just click randomly, but you really click on spam emails, eventually the system is supposed to improve its performances. There can be other problems like overfitting and so on, but we set them aside for the moment. Okay? And that is essentially what we want to learn. This is the object of the algorithm. It is not the document, one specific document. Once you have the classification function, you're going to classify all documents. What you really want to learn is this. Okay? Not how to learn one particular document. So, what it means is that at some point you will need a training set. Where do you collect it from? Well, either you collect it implicitly. If you're running an emailing service, you can do that. In other cases, you have a document collection, and you have, for example, a subset of the documents which have been classified manually. There is a large number of such collections which are available in the literature for use. Okay? Maybe at some point we could make a bit further on a practical exercise with a small collection, the 20 newsgroup dataset, maybe. So, before we move forward, I just would like you to appreciate the very large way in which you can think of labels. So a label can just be something describing a topic, finance, sports, and so on, or it can be something describing specific characteristics of a specific class of objects, like movies, or just something describing even the attitude of people toward a topic. And it's a very important case nowadays in which, let's say, sentiment analysis, right, has become so fashionable. People are using them a lot. I mean, people are using sentiment analysis to organize campaigning strategies, for example, political election, you know, and or they can be domain specific. For example, if you have YouTube and you want to avoid your children to run into videos with adult or violent contents. So, when you have, but at some point you need to build, as I was saying, your data set. So either you do this manually, this has been done largely in the past, it is still done today. For example, if you go on the ODP, which stands for Open Directory Project, you will find a large collection of web pages which have been manually classified depending on the topic, on their topic. It's a very, very good use and useful collection. It's a huge collection, actually, okay? It's millions of pages. Or then you have domain-specific classified databases, such as PubMed. So that's scientific literature in various areas of medicine, for example. Another way you can have, let's say, collections being classified, let's say, using as rules, as we have seen at the beginning. Okay, these are a number of examples I'm going to skip on, which are still used in some cases. Let's say Google Alerts is also partially based on queries, on standing queries that very often the user formulates to begin with, and then the system expands. And this is what we're interested in. This seems to be a panacea, so it is going to automatically classify for you. But then, as they remind us here, there is no free lunch, since you at some point have to classify your training set anyway. And the larger the training set, the better. Because have you ever heard of overfitting? Yeah, you know where it comes from? It comes from a very deep thing called the VC dimension. Ever heard of? Vapnik-Chervonenkis dimension? No, I know. Very often people talk about overfitting, but there is a very deep and not trivial and subtle mathematics below overfitting, which has to do with the minimum number of samples, the minimum number of samples that have to appear in a training set so that your classification method generalizes. It means that it is able to really correctly classify new samples, not in the training set, assuming that the training set and the test set are extracted from the same distribution. Okay, it's a problem on how large your sample should be. If the distribution of the training and the test set documents is the same, there is a size of the training set after which no overfitting is going to happen, but you have to compute it. Okay? And computing it can be non-trivial. And there is a number of interesting and deep results about this. But whenever you have overfitting, probably, it means that your training sample was too small or your hypotheses were too many with respect to the training set you have. Okay? So too many classes. So, just to say that no free lunch means no free lunch. The more, for example, hypotheses you want to test, the more classes you want to have, the larger your training set needs to be. Okay? So, another way to collect is what I was saying, relevance feedback. I think Professor Vitaletti will elaborate a bit more on this in another lecture. But relevance feedback is, for example, something that you do whenever you have an email spam filter and users can click on spam emails. Essentially, you get a relevance from the user. In that case, relevance means spam. Okay? And now let's come to naive bias. So the foundations of naive bias. What is the point? What is the simple idea behind this? So, of course, people didn't come up with naive bias text classification from all of a sudden. People have been working on these problems since the 60s, 70s at least. And to begin with, you come with very simple questions. You come up with very simple questions. So one first question you can ask is the following one. Assume that I have the very basic task. It's a very simple task. I have just two categories of documents, implicitly defined, relevant and non-relevant documents. With respect to what? It doesn't matter. It can be a query, okay? But in a way, whenever you have a query, you can implicitly define two classes of documents, the relevant ones and the non-relevant ones. Notice that I'm making the word simple, binary, right? I'm not giving scores. I'm just 1, 0. I just have two scores, okay? If you remember, this was the first, how should I say, the first type of retrieval we considered, Boolean retrieval. A document is relevant if it contains all terms of the query, otherwise it's not. And that's a type of binary relevance. And this is the type of relevance we are sticking to for the moment. Now, suppose that my task is so simple. I just have to decide with respect to some given query whether or not a document is relevant. How should I do that? Well, the only thing I have given a document is the words it contains, right? So the implicit assumption is always that the words, the terms a document contains and their frequencies should be correlated with the relevance or non-relevance of the document, right? Of course, there are a few words that are not providing a lot of information. For example, stop words, right? Very often. But let's assume, okay, we have removed stop words. Then you're left with a subset of potentially relevant terms that may or may not appear in the document with given frequencies, and then you try to understand whether or not a given document with certain frequencies of terms is or not relevant for the query. What can you do? Well, you can try to do my God, I hate this notation. It's horrible notation, but I hope the authors never. No, I mean these are beautiful slides. Otherwise I would not be using them. No, I'm not kidding. Only the notation sometimes let's say, have troubles with. Anyway, let's consider a specific term, and let's ask the following very stupid question: what is the probability? I don't know. What does this mean? It's a very shorthand for writing a more complex expression. This means the following. What is the probability that if I have a document in which the word dog appears, what is the probability that if the dog appears in a relevant document? This is what it means. Given that the document I'm examining is relevant, what is the probability that I will find dog in the document? Okay? So this is the first basic question one may be tempted to ask. Why is it a convenient question to ask? Because implicitly, you always ask questions about things that you hopefully can compute. It's pointless to ask a question about quantities that you are never going to be able to compute. And this is a quantity that you can estimate, right? For example, how could I estimate this probability? I could do just so I'm using an even worse notation than that one, okay? I could just consider the number of documents which are relevant and that contain the word dog in my training set divided by what? The number of relevant documents. So, what is NR? Consider V is the vocabulary. Consider every possible term. Take the number of documents that contain, of relevant documents that contain term T, sum over all possible terms, and you will contain the number of relevant documents. Okay? This is NR. So, take the fraction of documents. Actually, in that case, that was wrong. I was over counting. But so don't copy that. That expression I wrote, I should have written something else. That was wrong. Okay? Don't consider it. I just have the total number. This is correct. The total number of relevant documents. So essentially, the fraction of relevant documents that contain the word dog can be, as a first approximation, a decent estimate of this probability. Okay? You see that? So, it is very interesting that some intuitions, this is just an intuitive argument, right? Why should it be like that? Well, there is a hidden intuition that if we sample documents uniformly at random, essentially this probability is going to be estimated with this estimator. Okay, so there is some statistics behind. We are not going this beyond the scope of this lecture at least, but there is some reasons to do this. Okay, so this is not necessarily this probability. These two quantities are not the same, so I put an equal, but that's my conjecture. Okay, this is actually my conjecture, that this is a good estimator of this probability. So it is something I could try to estimate. If I could collect these estimations for all terms, then perhaps I would have a principled way of deciding, in principle, I would have a principled way of deciding whether or not a document is relevant or not. What could I do? Well, what I could do is just to collect, given a document, I pick all the distinct words the document contains, and then I try to compute some function of these probabilities, which I'm estimating. So the higher this function, the more likely the document to be relevant for me, right? So basically a document is probably relevant if it contains many words for which this ratio is relatively high compared to the rest. That's a basic. At the same time, of course, you can compute this. Okay, you could try to do this again. So this is a very, very basic idea. So, and proceeding bottom up, it will take us somewhere perhaps. But with this very simple idea, we in principle have a way to quantify how potentially important a term could be for a document. I mean, how potentially important let's say a term could be to decide that a document is relevant. Okay? And notice the other point is that these are quantities that we can at least estimate. Actually, these quantities we can compute. And computing these quantities, we hope that we are estimating these probabilities. Okay? Good. There is, let me see. Okay. There is another thing that we have to say, which is so obvious. I will ask now a question which is very, very obvious. The question is obvious. The answer is less obvious. The question is the following. Okay, you told us that you want to estimate this probability, right? Whenever you take a probability, there is a sample space. Yeah? You see that? Probability means sample space, means an experiment. And then the outcome of the experiment should be a term. Huh? What is the experiment? What is the sample space? How am I taking this probability? I am estimating it in this way, and this way looks very, very obvious. But what is the experiment here? What is the sample space? Never thought of. What is the sample space? What is the experiment I'm running when I'm considering this probability?
Training data.
The experiment. What is the experiment?
Training data.
I don't. Can you speak louder? I am.
The training data is the sample space. Right? The input.
No, the training set. The input is the training set. It's always the training set. Yes, I know. It's the training set. We are working with the training set to estimate those probabilities. But now the experiment I'm taking when I'm thinking of that probability. What is the experiment?
The probability of a given class, given the term.
The class is just relevant or non-relevant.
A random variable.
A random?
Random variable.
Well, of course there is a random variable. And the random variable, what is the random variable? Good, you're coming closer. What is the random variable here? So I'll tell you which is my experiment in this case. Next time I ask you the same question, you will try to answer. The experiment here is the following. I have my collection of training documents, so which are already classified as relevant, non-relevant, because I have hand classified them. And now I'm picking one relevant document, let's say uniformly at random. And then I'm asking, does the document contain the word dog or not? So that's your random variable. It's a Bernoulli variable. It can be 1 if the document contains the word dog, otherwise it's going to be 0. If you think about, if you're doing this experiment, that is your distribution actually. It's a uniform distribution, right? So that's what you will get as a result. That's exactly the probability. Okay? So, then why did I write, I didn't put an equality here rather than approximately? Because if that is my experiment, this is exactly the probability. Okay? I didn't put an equality here because normally, as we will see in the coming slides, when you consider Bayesian inference models, normally you try to work with respect to a hidden model of document generation, which may not necessarily be a uniform one. Okay? So this is just, so it is a way of estimating this hidden probability. It's not exactly, this does not necessarily describe the way in which documents appear in a document. So this is essentially telling us that with this frequency, if a document is relevant, it will contain the term. Maybe the picture is a bit more complicated than that. Probably there are correlations between the terms and so on. Okay? So this is our final goal, but I guess at this point you have understood already. So, so this is just to make clear that that is what you want to compute in principle. You give me the document, I give you the class. In practice, there is a difference in that the document is not what you give to the function. You give a representation of the document. It could be a bag of words, weighted bag of words, binary vector, whatever. Actually, bag of words and binary vector is more or less the same. And we have gone over this. And now, at this point, we go back to bias. So at some point, some people were sitting trying to figure out how to classify documents, and then trying to play with bias. I mean, eventually they realized they were playing with bias rule. Why? Let's try to figure out in probabilistic terms, what it means to classify a document. Okay? What is my input? The document, right? What is my output? The class. So, in probabilistic terms, I'm trying to give a confidence to the document. So, given this document, what is the probability that its class is C? That the class I'm looking at is C. So, what is the probability that this document is a representative of class C? Is it clear, the question? How do I write this in probabilistic terms? This is what I'm given, the document, or better, its representation. And this is a class. So this is my random variable. So notice again, I'm writing a shorthand because I should write this like the class variable. The class of the document is C, given that doc equal to D. Okay? Something a bit more complicated, but very often it's common you use this type of shorthand. Good. Now, do you agree that this is what we would like to compute, right? But this is what we have. So, we apply again Bayes' rule. I have already forgotten Bayes' rule, and I have to deduce it every time. So, good exercise. No, sorry. I was writing something absolutely wrong. Okay, this is what I want to compute. And what this is telling me is that in order to compute this, essentially I need two types of information. First of all, the first type of information is what is the probability that if I pick a document, it belongs to class C. Okay. The second type of information is what is, if the class is C, what is the probability that I will collect document D? This is a strange question. If I present it like this question, what does it mean? You have one document, so you know that it is of class C. What is if you're uniformly picking one document from the documents of that class, the probability of picking a specific document is the same for all documents, right? If you're picking uniformly at random. So it's strange. So perhaps this is not the right definition. Here is where really the model comes into the picture. Okay? So, when you study these things actually, and you define this probability, again we have to do the same exercise we did 10 minutes ago. So we have to ask, what is the process I'm describing? What is the probability taken with respect to? This case is less simple than the other one. How am I taking probabilities here? The probability with respect to what? Have you an answer? Because otherwise it really doesn't make sense. I mean, this thing here written, people normally learn these methods, taking these things for granted. Probability, I estimate this probability in this way, and then I apply certain rules. Fine. What is this probability? Have you any idea? In your machine learning course, did you learn what this means? This P, what is P? P taken with respect to what? Is it clear what I'm saying? What is my sample space, for example?
If I have a set of documents, sample, and I know the classification, that probability is much more easy than the first one.
Wait. So you have a collection of documents?
And the classification of every document, that probability, the conditional probability in that fraction is much more easy than the first one.
What is the first one? Then this one?
Yeah.
Yeah, okay. Here comes the model. So when you use a probabilistic model to infer something, like when you apply the Bayes method, normally the assumption is that there is some hidden probability distribution that generated your collection. What is the probability distribution? It's people writing documents, for example. Okay, if you consider this process, I have a training set collection, right? What are these? Let's think for the moment. I have collected a training set of documents, any document, newspaper articles, for example. Now, these documents have been generated according to some probabilistic process. What is in practice this probabilistic process? It is people writing down documents, right? Just I do not know what is in the minds of these people, why they use a certain word, not another. So to me, that is just a probabilistic process generating the documents, right? Actually, these people, but even the people themselves have no clear idea why they use a certain phrase rather than another one, if you ask them. So to me, it's a probabilistic process. So what is this probabilistic process doing? The probabilistic process is generating documents. Okay? So what is my sample space? My sample space is simply a collection of points in which every point is a document. That is my sample space. Okay? So, and this sample space, let's say it is potentially very large. Because I have a number of documents that is potentially infinite. Or let's say it's finite just because human lives are finite. But let's say it's very large. Okay? That is my sample space. Now, how is a document generated? Well, actually, we don't know, but we can try to figure it out. Let's say a generative model to produce a document. The generative model might be of the following type. First of all, decide which is the class of your document, the class the document is going to belong to. Okay? I'm not saying that this is what people do, not at all. I'm just describing a model that is intended to describe what happens in reality. It's like in physics. I mean, in physics, you also model reality. I mean, the model is not reality. I mean, the model is a model. It's a theory about, it's a description of reality, right? So we are describing a description. We're describing how people produce documents. And of course, we would like to come up with a description, so with a model that is not so complicated that we cannot compute its parameters, right? So we try to come up with a decent model, with a good model, and we will see that the models we use are actually, they perform well in practice. But this model should still be manageable, computable. So let's try to come up with a general model. So the model will do the following. First of all, select a class. So select the class the next document that is going to be generated belongs to. Okay? So this is not so naive, actually, because whenever you're writing, for example, to write a news article, actually you're writing about a topic, right? So implicitly, the moment you sit down to write a news article, you are picking one class. Yeah? So the document is to be in sports, politics, or whatever. Whatever the underlying class partition, the document is going to belong to one class. Perhaps more than one class, but let's stick to a simple case for the moment. Then you're going to generate the model, the document. How are you going to generate the document? Actually, you had to generate the contents of the document, so the words that appear in the document, potentially in which positions they appear, right? This is a generative document, a model of the document, okay? And this is assumed to occur according to some probability distribution. We don't know the probability distribution. We'll try to make some guesses. But in principle, the probability distribution, according to which you generate the document, is reflected in the training set. You see what I mean? The documents, if the documents in your training set were generated from this unknown distribution, let's say the frequency of terms in these documents, depending on the class they belong to, the frequency of the documents of a given class will reflect this hidden probability distribution according to which the document was generated, right? That is why you are taking statistics on the training set to try and estimate these probabilities, okay? You see, we are getting closer, okay? That is what you're doing. So remember, whenever you have a Bayes classification model like this, you are implicitly assuming a model whereby documents are generated. I have not been very specific for the moment. I will be more specific later. But it's important for now that you understand that this is the way in which one thinks. Otherwise, these probabilities have no sense. I mean, these probabilities are not even defined. I didn't define the probability. Whenever you define a probability, you need to implicitly describe a process. Otherwise, what is the probability? It's nothing. It's a P. It's a symbol. So I should, in order to use them and to estimate them, I have to say what is the underlying experiment I have in mind. So which is the process according to which, in my opinion, documents are generated. Then, at that point, I can give an expression for these probabilities, perhaps, and try to estimate them from the data I have. Is that clear? Huh? I hope it is. It should become clearer and clearer as we proceed. Now, let's try to make this a bit more concrete, and then I will stop. Okay? And we make it a bit more concrete with one specific model to begin with. So we have to compute certain parameters here. If we want to estimate this, we need to estimate this and this. Before we estimate these probabilities, which can be a nightmare, perhaps we need to elaborate a bit more on them. So what is this probability? What is a document? In principle, a document will be a collection of tokens where every token is a word, contains a word, right? Let's assume that the document has n tokens, for example. Okay, in this case, my document would be I have I in first position, go in second position, home in third position. This is one possible representation. Another representation will be the following. I have a binary vector, huge binary vector, with one position per possible term appearing in the document, and I will have a 1, Okay, these are two possible representations of a document. Which one is better? We will see. Okay, but for the moment, let's say I'll begin with this one. So it is a variable length vector in which every entry identifies one term with its position. Okay, so if I have a document with n terms, I will have the description will be a vector with n entries, and each entry is a term. Okay? These positions, for example, in this case, the document will have x1, x2, x3. x1 will be equal to I, x2 will be equal to go, and x3 will be equal to home. Okay? Just to be clear. Is this helping us? Let's see. So, the category of a document. The category of the document I am not very pessimistic about. Because if you have a training set with, let's say, which is already classified, you can estimate this probability with, at least a rough estimate, the fraction of documents that belong to C in the training set, right? So the results about sampling I was telling you about guarantee that if I pick a sufficiently large training set and the documents are generated, let's say, independently of each other from the same probability distribution, at some point I will be able to track this probability fairly well. So I don't worry about it for the moment. I should worry about this one, but we will see that this is not actually important, luckily for us. Let's worry about this. But that's the same. It's not really the same. Okay? So, what can I write about PDC? Given the first model we have, yeah? So, this is the probability that I find some term in the, not some term, that specific term I'm observing, because the document is something, okay? It's the probability that I'm observing that specific term in the first position, that specific term in the second position, and so on, until the last position, given that the document is of category of class C. This is a probability. What's the problem? We can do that. In principle, yes. I could try to estimate this probability. You know how? I collect a training set large enough that I can estimate the frequency with which I find this term in the first position, this term in the second position, and so on. That's a bit problematic. Let's say in theory, I could estimate this probability. In practice, the number of samples I need is exponentially large in a lot of things. For example, for a document with n terms, from a vocabulary of size of, from a vocabulary V, you know which are all the possible, if the document has length n, provided that n is also generated from a distribution. I have to know, documents have not the same length, right? So in my document generation model, I first choose the class, then I pick n, I generate n, conditioned to the class of the document being C, and then I generate a document of length n. Okay? So how many potential documents of length n do I have? There are a lot. You have n entries, each of which can take a value from the vocabulary, right? You know? 2 to the n. That's a lot. Let's say 40,000 terms. We don't want to... a document with 1,000 words? No, that's not something we're going to do. Okay? So this idea is not going to scale. So in principle, we could, if we had the age of the universe at our disposal, perhaps, but in practice, this is a nice formula, but we have to work a bit more on it. Okay? And we're going to work on it in, let's say, 15 minutes from now. if it's okay to you. Hmm?